Okay, great. All right. Okay, hey everyone. Let's see if I can move this. Actually, can I just make that go away? I don't care what I look like. All right. Hopefully I'm somewhere in the view. Anyways, my name is Tim. I come from a company called May Mobility. And what I'm going to talk about is robotics mostly. I'll talk very little about DataFusion at the end, but really want to talk about what I want to lay out is how we do data science and robotics, and then where I think that, and I'll give an opinionated view at the end of where DataFusion fits into the picture here. All right. Just again, basically going to go over a little bit about robotic systems because I suspect that I'm talking to a slightly different audience than I normally talk to. I'll give out one specific example of like a real world problem I have to deal with in my job, and some of the problems and the approaches that we take in robotics. And then finally, hopefully, which will be the crux of this session. So like, how am I in any way qualified to talk about this? My background, I'm currently director for SIM and infrastructure at a company called May Mobility. It's a autonomous public transit company. One of my coworkers is actually here with me. My group works heavily in data engineering, feature generation, and I'll talk a little about what that might mean. And I'm trying to use data analytics to validate our safety case. So we're one of two companies that operates fully autonomous, like no driver in the front seat at all in the United States on public roads. So in order to do that, you have to have a very solid safety case, and we use data as a big argument for that safety case. I have some past work in here. So at Sora Technology, I worked on off-road robotics, right? And that heavily influences some of the things I'm going to talk about here. And then before that, industrial robotics, whatever, University of Michigan and the US Navy background. But all right. So when it comes to robotic systems, I'm specifically talking about modern robotic systems, which are usually a system of systems. I'm not talking about industrial robotics. So like if you go to Ford manufacturing plant, you see a 6-DoF robot arm on a conveyor belt. I'm not talking about those. They work a little differently. I could talk about them, but I want to focus on modern robotic systems, which are built of larger things. So usually you have something kind of like the picture here, where you'll have multiple nodes. These are just usually separate processes that are running. I mean, just usually separate executables. Some are Python scripts, some are C++ programs that have been compiled. And there's usually some form of messaging infrastructure, right? So it's either a publish and subscribe service or a query response service. But the important message to come out of this is that like how these different nodes that are doing all these different things, and we don't use ROS, but ROS is a good example because it's one a lot of people, especially if you come from academia, are familiar with. But you've got all these messages that are flying around from all of these different processes. They're all running asynchronously. And, so some of them are like coming from a sensor. Some of them are doing some data processing, and you've got them coming in all the time, and you've got all these things going on, right? So usually you have three things you have to keep track of. Actually, we were talking about this before we got started. Like you have a communication layer, and that is just kind of what is the middleware that is allowing data to flow around the system. You have some kind of message definitions, and these are relevant when it comes to data processing. And I'll get to that in a second. And then usually some kind of like serialization and deserialization protocols that go in there. All right, so this is just like very, very robotics 101 stuff. So, and then we'll plop on some kind of data logger at some point in the system. And something to know is that the place you put your data logger might be on a disparate computer than what is going on. In actuality, you usually want that. If it's a safety critical system, you want the things that are looking at the system to not be able to influence it, right? Like you want your safety critical components that have all been validated for their safety case. You can't touch them. So anything you want to put on top of them, whether it's logging or debugging infrastructure or anything else, you usually want it like physically separated if you can, or some other way. Sometimes you can just containerize it and say it's good enough. But you throw a logger on there somewhere. And the crux is there may not be any guarantee about timing. And timing is critical to data analysis for robotics problems, okay? There's also no guarantee about what does time, the current time mean to any one of these processes that runs. There are some processes that say, hey, I'm super fast process. What really matters is not what time I think it is, but what time I got the thing that told me to go process. So you'll have some process, and it's like a good example would be, let's say I wanted to do a process that's gonna spit out what is my visibility from my current position, right? So it receives a message from the cameras or the LiDARs or some sensor, and it's going to analyze that, and it's going to say, okay, from my point of view, I can see this far in this direction, from myself. But it doesn't matter what time I processed it. It matters what time the input came to me, right? So because this output is correlated to that time input. So this process might do that. A separate process might say, the thing that's really important to me is what time is it right now? So I'm going to look at my wall clock, and that's what I'm going to go off of. And then some others might say, I actually don't have good timing information, but I know someone else that does. So my timing is whatever they tell me it is, right? And these things do exist in modern robotic systems. They exist and they coexist, which makes timing and understanding timing to be a non-trivial problem. So in the end, you end up, you run into the system, you go out and you run your robot for a while, and you're generating data. Common logs, so common logs, of course, is going to vary with the type of system you have, right? If you throw on 3 more LiDARs and 10 more cameras, you're going to have, 3 times or 5, you're going to have a lot more. But for just a figure of merit, you go run a robot for an hour, you're going to get somewhere between hundreds and 1,000 gigabytes per hour of data, total data. Just a picture of like what I'm talking about. It's my company, so this is like really what we have, right? We have a GPS antenna somewhere that's telling us where we think we are in the world. We have a LiDAR, a laser. I forget what it means, but it's a dimension and range. Yeah, I don't know what the I stands for. But so you have multiple cameras that are going out there. They're seeing the view. You have additional LiDARs in the back, sides. You have an accelerometer, an inertia measuring unit usually. You have some actuators around the brakes, the drives, wheel angles, and things like that. So you got all these sensors, and then stuff internal to the cabin as well. So you can talk to people, riders, like, hey, what's going on? All right. So here's a real case. I want to know how well does my perception system work? As a safety case, one of the things that is very difficult is to say, is it safe for my car to go or not? I only know it's safe to go if I have a valid understanding of how well I can detect the dangers to me. Like, so in this case, a cross traffic. So if I'm the white car and I'm coming up to the stop sign, there's a blue car who doesn't have a stop and they're blowing by. If this is a 10-mile-per-hour road, I can see them pretty late and it's safe. But if this is a 45-mile-per-hour road, I need to see them pretty far out. Okay. So and this is a problem, right, I have to solve. So one of the questions we say is, how far away from us can we identify them? And I can't just do this by like writing code that's going to run on a single log, and it doesn't scale, right? Like, why do we do data at scale? Like, we have to be able to do this at scale. I've got thousands of logs coming in every day. I want to process them all. I want to know, does this happen at just this site? Does it happen at every site? Are there specific locations where I have low detection ranges? And really want to know is, exactly how far away from us do I positively get the right identification of that vehicle? Is it a car? Is it a truck? Is it a bus? Is it a person? Is it a scooter? Like, that's what I want to know. How far away from me? So what do? I might combine GPS data with map data to figure out, because what I really care about is, as I'm coming up to this intersection, how far, once I get to it, can I identify that cross traffic? Now, if I'm coming to a stop, it's a safer case, but if I'm coming to a case where I don't have to stop, there's other people coming, I really have to know, because that determines my reaction timing. Because if someone blows their stop, I need to know how far away can I detect them so I can break, like, these are all safety case type stuff, right? So if I want to do this, and I want to do it by type of agent, because I want to make sure that my classifier is working right, because I respond differently to cars than I do bicyclists or pedestrians and things like that. So I want to know, how am I getting it right? So I need to know what's correct, what's real. This is easy because I have data and it's after the fact. So I can just look through and I could say, all right, well, I'm going to track that agent and by agent, I mean the other whatever it was. I'm going to track it and find the time at which in any of its lifetime that I got the highest maximum likelihood that classified. I'm going to say, okay, well, now I know what the highest maximum likelihood is. Now I can apply that back to all of the history I have. And so what am I doing here? Like from a data perspective is I'm probably group by and then searching for maximum, applying that maximum to the entire group, and then going back and saying, all right, well, now find the earliest time at which the maximum likelihood equaled the correct classification and didn't change after that, right? Because it's not that I just got it right once. I wanted to know at what point did I stop getting it wrong, right? And that's an important, so one of the problems is this is an important difference between some of the approaches I've seen taken by just data scientists and roboticists is like the bullet point or the bold here is that all robotics data are noisy. You have to build into your approach from the beginning how to handle these things. And then you might do all kinds of summary statistics, right? Like, based on type of agent, like how differentiable it is, because like, oh, you finally get it right, but you said it was like a 30% chance of this and 32% chance of that is not particularly differentiable. So like there's a bunch of other stuff you might throw in on top of that. So, all right. So what makes it hard? Noisy data. Like seriously, that is the biggest problem in robotics. You get a processes crash, buffers, whatever. One of my projects, tree branch fell on the antenna. The antenna was no longer there. Data still kept coming in from the process that was running the antenna. It was garbage. How do you, if you don't have a person there to like point that out, how do you identify that after the fact, right? And then there's like getting the data into a data store. And this is where and I'll talk about most of these independently, but this is just a computer science problem. I have bits of type X, I need them into bits of type Y, ones and zeros, right? How do I convert these into those? The naive approach is often just hand encode them. That is not very scalable. Another problem is transforms. So sensors are dumb. Sensors, you want them to be dumb generally. You want the sensor to say, this is what I can sense, which usually means that it's from my perspective as the sensor. So if I have that LiDAR on the top of the vehicle, or I have that LiDAR that's on the front left bumper, it sees the world in a different way, and I have to do a coordinate transformation to get back to egocentric frame, right? So you have these reference frames. And then, like, not in this kind of vehicle that I showed, but in other ones, like, let's say I had, we had a bomb robot, right? Where so you drive the robot to the bomb, it's got an actuator arm, comes out, disarms the bomb, that kind of thing. Well, the end of that actuator has like 3 joints between it and the base of the robot, right? So if I have a sensor on it, which I do, like a contact sensor on the end of it, where that contact sensor is relative to where the vehicle origin is constantly changing in time. So I might have 3 or 4 different coordinate transformations that are also dynamically changing in time that I have to account for. You also have noisy data, if I didn't mention that. There's spatial analysis. So the problem with spatial analysis is, I'll talk about it in a bit. I think that is one that at least people I work with, have struggled a bit in database approaches. And I'll get to why that is in a second. And then, going back to that question of timing, like, how do I make sense of this timing information that comes in from all of these different, these different things? And seriously, the data really are noisy. Probably the best example of that is was back on that off-road robot program. We were doing a final demonstration, and it was winter in Michigan, and there was snow on the ground. And so in the robot is the safety operator and then myself collecting data. And we're coming down this hill, and it's iced over, and the robot has the brakes full on, the wheels are locked up, and we're just sliding down, heading right to this tree. And we're sliding down it. But the problem is the wheel encoders are encoding 0 because wheels are stopped. So the wheel encoders say I'm not moving at all. The IMU is giving me a very different, inertial measuring unit is giving a very different thing. It says I'm moving. But if I also have taken a naive approach, which I've seen many times done, both in my companies and other places, they're probably encoding that IMU to think that the Z direction is down. But if I'm on this hill, there's a projection that I have to do, right? Just geometry, right? Like high school geometry, I have to do a projection to get the actual direction of travel, right? So like I probably have 2-3 different sources of error coming in. And so these are just challenges in robotics. And the question is like, how do we deal with them now, and how can DataFusion help out? All right, so getting data in. So like, for example, let's say I have a sensor and it's putting out an image. So that image is going to have a header. That header is another message. It's going to have additional information. It's going to have a timestamp and a whole bunch of other stuff. And it can have arbitrarily deep structure, right? Similarly, like a GPS. So I'll have, the point of having a couple examples here of different messages is that when you look at data coming in from a robotic system, it is typically going to be very highly structured. Some of the cases of this do not map well or easily into what you might look for in a table or something like that. Okay. Again, there's two general approaches. There's publish and scribe, query response. You have to think about that. So one of the difficult questions that we've had in practice is like, how do I get this into a format that is usable and can do fast queries over, right? Because I don't want, like, I can just take it and dump it in, right? I could just turn it all into a JSON and put it in one field, right? With a time on the beginning, and then say it's someone else's problem to deal with analysis later on, and it's in. But that's stupid. It's naive. Maybe it's not. It's naive. So can we build translation, right? And then the question is, at what point, and this is just something you have to deal with, it's like, it's not particular to DataFusion. Like, at what point in that process do you switch it from something that's closer to the raw original or into something that is more friendly to doing fast queries and fast processing? So trivial example, position, right? Let's say I have a robot and I'm in a Cartesian coordinate system, so I've got X, Y, Z. It's typically going to be encoded as a fixed length buffer of floats, three floats, X, Y, Z. Should I just leave it like that, or should I convert it into 3 columns of position X, Y, and Z? Right? The advantage of doing one is that I can, do, like, if I want to bound it to some things, say, hey, you know what? Let's only process the data when we're above certain altitude. That helps for like UAVs, drones, right? It's super helpful. Like, I don't want to process anything when I'm launching or landing or on the ground. Cool. So if I do that, then it's very helpful that I've converted into separate columns, because now I can probably fast query that out. Otherwise, I'm indexing in or doing something like, and these things matter for like especially when you try to process at scale. And then, okay, so the other bit is when, I don't think this is super special, but you might be doing real-time ingestion, you might be doing after-the-fact ingestion. And there are slight differences to how you deal with that, because like real-time ingestion, do you take the time that it was received? Like, what about queue sizes and things like that? After the fact, well, now you're based on the logger. Like, there's just things you got to think about and deal with. But this is just, this is the bread and butter. And then if you want to, if you want to do something, so this is like real LiDAR data, like from, no, this isn't one of ours. This is a picture I found on the internet. I know what our stuff looks like. It doesn't look like that. So I have a LiDAR. So LiDAR is nothing special. It's a laser, spins around, and it's measuring time of flight return based on time of flight. I do a little physics, and I have distance, and now I generate points, right? So I have a whole bunch of points. You call it a point cloud. And these are these are where all the things are out there, all right? So those point cloud is going to be relative to the mounting point of that LiDAR. But what I really care about is, what is it relative to the origin of my vehicle, which is going to be defined somewhere. Like for us, it's the middle of our rear axle. For another one, it's like where the antenna is located. It's going to be defined somewhere. So you have some kind of transform, and no kidding, a lot of times it's a person with a measuring stick going out there and measuring how far along the axle is, how high up is it, or something like that, and then you define it, and then you have some kind of transform. Annoyingly, transforms are not always done the same way. So you have to figure out, like, do you rotate first? Do you translate first? I wish there was, like, I've just been in the business long enough to know that it is not uniformly applied. And then the same company might not even uniformly apply it in the same way. So you got to figure these things out. And the problem is, and now I'll get to like DataFusion. These transform operations are not easy. They're not easy to write. Like if you write one in like PySpark, it is ugly. I mean, it's just math, right? It's just a 16 by 16 matrix in the end that you're just doing a little math over. But it is, and you could say that, and it sounds glib, but in practice, like in practice, number one, not everyone has the math skills to know that you've done it right. It is linear algebra is non-trivial, and trying to do linear algebra like in a data frame, like it's misery. My experience has been misery. So and I'm actually someone that's like pretty decent at it, and I find it to be miserable. So all right, so another problem. How do you deal with spatial analysis? Like, again, for this question of like, when do I first detect them? I actually often care about it's not just about how far away were they. What really matters is how much time do I have to react to them, right? So I need to do things like spatial temporal analysis. I need to figure out from the path that I'm taking and the path that they're taking, what is the point of intersect? And then I have different acceleration profiles. Like, the world is dynamic, right? So I need to figure out not only like where is our intersection, but what is the time? My time of arrival, their time of arrival. What about the time to clear? If they're going to go in front of me or behind me or things like that. So as robotics engineers, we actually have a ton of tools for this. Like, we've been doing this for a long time, and it's great. But they don't necessarily map well to database operations. There are three that I'm familiar. Well, two I'm really familiar with about how one can go about applying this. GeoPandas is probably the best in my experience that is out there. Now, Sedona, which is doing Geo and PySpark, is also good. It's actually one that we use. And coincidentally, yesterday I was talking with the author of Sedona because they have a company called Where Robots, where they do they have a Sedona replacement that operates much faster at scale. And as I was chatting with them, they were like, "Oh yeah, our next release is going to include DataFusion." And I was like, "Really?" And they're like, "Yeah." I was like, "I'd love to talk more about it, but we had business. Like, I had to do company business first and foremost, and then we ran out of time and I didn't have." So in our next chat, I expect we'll talk a little more about that. So there's going to be something, because they're not going to have Sedona based on DataFusion. That's not going to exist, right? They don't have the libraries necessary yet, but they're going to have some part of their system. So that's interesting. Like, it was just at 1 o'clock yesterday, it just happened to come up, and as we're talking about, what they might be able to do for us. And then GeoAero RS. So this is a newcomer, and this person named Kyle Barron, he's a member of DataFusion community. He's pretty active member of the community. Is working on that, and I think that's going to be extremely interesting to see if we can get GeoAero matched into DataFusion. That could be really cool. And then there's this additional problem with robotics with geodata. We don't have a good native storage format for geometry data, and this may be because the geo community has made a decision. And we could get in, like, maybe in the breakout sessions we could talk about why this is, but generally right now it's encoded as either well-known text or well-known binary, which then means you can query it, but you have to now decode it in some way, which is not super awesome for things at scale. Again, time synchronization is one of the most important features on doing robotics systems. So I don't think that there's a good answer to how one does this, except that you have to establish standards within your organizations that are doing it about what does each time mean. And as a data scientist or a data engineer, you have to pay a ton of attention to making sure you get this right. Because if you get this wrong, you can't trust any of the results that come after it. And I don't know if because really it's about like I've got these messages coming in at different times. And, like I have this one that tells me where I am, and I have this one that tells me, I've gotten a detection of an agent. Like, what if I put it up here or there? It will change how I analyze those results. Okay. So my opinionated view, if you want to be successful in robotics, you must cultivate an attitude of distrust of your data. The naive approaches that people often immediately grab are thresholding and say, I'll just threshold. That's cool. I'm not a betting person, but I will lay a bet that wherever you throw your threshold is where your problems will be, because that is what is going to happen. Because you're going to be an intelligent person and you're going to put a threshold at a boundary that matters. And that's where your problems will be, right? Like, perfect example. I did this in one of my jobs. I needed to figure out when the robot was moving, because when the robot actually starts to actuate and move and get going makes a difference in how I should respond to things. I was at a military program, so I was like, how I respond to threats is different if I'm stationary versus mobile. Okay. And I was like, cool. Once I start going like 0.1 meter per second, I'm moving. It is the wrong answer, right? Because that's what's going to happen is I get the creep thing where I'm like, oh, I just barely figured I was going 0.1 meter per second. Or I'm actually creeping at 0.1 meter per second, which means I'm getting 0.9998, I'm getting 1.001, getting 0.97, right? Because there's a real range. So I cannot just threshold, which is the first thing everyone jumps to. Smoothing helps, but dynamic boundaries are a far more robust solution. I need to build in detections for known problems, loss of data and duplicate data. Those are the big ones that come in. And I need to build outlier detection. And this one's hard, right? Outlier detection is hard because I need to understand the problem well enough to know that I've been able to identify an actual boundary condition or an outlier. Or maybe I just need to do some data analysis to identify what does it mean to be an outlier. And again, this is like how to handle errors. This is a top line problem. The actual big problem I run into is that when people start doing data science in this case, they often don't think of it as a top line problem. They think of it as something to tack on at the end. And from my experience, that has been a big mistake. Big mistake. All right, so one more slide, I think, and then I'm done. Which is to be very quick. I don't use DataFusion in my company yet. That's a big yet. I'm trying to play the long game here, and I do want to get there. So just, and you can fight me over this, but Python is the language for data science. It is not Rust, okay? Data frame APIs are the language for data science. Fight me if you want. I don't even like Python, but it is what the community uses, right? And if we want a solution that will be adopted by the community, I do believe we have to meet people where they are. And this is what they are doing. Overwhelmingly, it is PySpark. It's like, if you want to do anything at scale, it's the game. It's right now, it is the game, right? We'd like to change that. Pandas is the game for single node. Like, I think Polars is way better, but everyone uses Pandas. Like, this is what people are using. This is the competition. So if we want to compete, in my mind, we have to have comparable functionality and some clear advantage over the others, right? And here's where I think it is. Rust-backed Python UDFs. I think that's the killer feature. I think that is what, when I try to convince people that they should, like in my field, that they should care about DataFusion, this is why. And I'll go back to that question of transforms. Writing that coordinate transform is messy. I already have excellent libraries that already exist in Rust. Phenomenal libraries, high quality code that already do it. All I need to do is just say, oh, I need to map these columns to those columns, or these sub entries in this one column to those, and put the output. And then I don't have to have this enormous mess of spaghetti Western code just to get something that will run at native speed through, PySpark, the JVM, just to get something that will run at native speed. Because what I really don't want to do and maybe, I don't know if everyone's familiar, like the thing that will kill you and user-defined functions is making the gap from whatever the native language is into Python data. That's going to kill you. That, like, you're done. Which is why everyone says avoid UDFs, avoid UDFs, avoid UDFs in PySpark as much as possible. You write these massive things just so you can avoid writing a tiny UDF. And it's because I can't. But with DataFusion, I can do this. I am doing it, actually. You know, I can write something in, and interestingly, when I write these UDFs, I don't even need DataFusion as a dependency in the library. All I need is Arrow. Yeah, I have two dependencies when I do it: Arrow and PYO3, which is the Python binding for Rust, which is really neat. It's neat for me. And then and here's where I think this matters, because number one, a roboticist and a data science, it's a different skill set, right? When I talk about doing these math transforms and doing the data analysis about, or doing the boundary conditions and identifying the problems, these are things that roboticists have a lot of experience with, and some of them are very difficult to do in data frame approach, you know. And I actually have lots of libraries. I have a lot of stuff already for dealing with these problems that have been, they're not new problems. We've been doing them for a long time. But roboticists are garbage at doing big data analytics. As I speak from experience. I'm learning, but like it's just it's a completely different skill set, you know. So, and here's where I think it fits in, right? So like I can separate concerns. I can have a layer of abstraction here where my roboticists can write the UDFs in a way that they can understand. Imperative programming is their bread and butter, right? And then I can package that up as a reusable analytics toolkit and hand that off to my data scientist, and they can say, oh, I don't have to think about how it works. Hopefully, I can just, you know, we have enough unit tests and things like that around it, and I can take away, I can leverage that toolkit. So what I get, highly performant functions, they're operating at native speed, and then keep that separation of concerns, right? Keep the data scientists working on data science, keep the roboticists working on the robotics work. And then, you know, my kind of last plug here is we've got a lot of good going on. But if we want to win, like if we want to get back to this first question, I would love to have one data frame API that I can use as a single node or at scale, right? So and so if I use DataFusion Python, I can do single node. I can't do it at scale yet, right? Which means I can work really well on a smallish set of data, but I can't go to petabyte levels. Done, right? So there's two projects that are under heavy development. Like every day, I don't know if he sleeps, but the person working on Ballista, every day there's just a ton that he's just done. And then DataFusion Ray. And I'm curious which of these is going to win. You know, we might have both, but one of them might win. So they're both under heavy development, both within the DataFusion project umbrella. Oh, I guess I might cut more. I didn't realize I had another slide. Okay, so how could this address those? Getting into the data store, I don't think DataFusion's a win here. But here's the thing. My work on DataFusion got me deep into Arrow. When I looked at the problem of data ingestion we had at my company, I said, I think we can do that differently. I think if we just dive in deep enough, we can redesign our ingestion system. I wrote it, took me 2 weeks to write it. It's paying my entire salary off, the amount of money we're saving from that data ingestion. By switching from a vendor-provided solution to one that is in-house, that is just narrowly, it's tightly coupled between our log system and how Parquet files are structured. So while DataFusion itself doesn't necessarily, working in DataFusion had a big payoff here. So the transforms, easy win. I think this is an easy win. Like just dealing with those. Again, the code already exists. It's about take this, put it there. In fact, I've done that at my for a toolkit that I've been working on for my company. So spatial analysis, I don't really have an answer here. I'm hoping that GeoArrow is the answer. There's also a question of like, oh, could we build in extension types? I don't know if that's the right answer either. Like, and this is about like how one stores data in the Parquet table or whatever. You know, if we have extension types, you know, that we could extend them with these geotypes. I've seen problems with that in doing it in PySpark, where you now have a table that's just not readable by anything that doesn't also have all of those libraries installed as well. So like I have concerns about that, but that might be, I don't know. The time synchronization, there is potentially a win. Right now, the way we do it right now is we like, let's say I have these 4 or 5 or 6 different tables of data that I need to combine so I can do analysis in one spot on them. Right now, I'm doing some kind of merge, a join. I'm sorting on the time column. I'm filling forward empty data, and it's fine. But I run out of memory problems. Like when I try to use DataFusion, I run into out of memory problems on this. But since I know that there's like a very specific thing I want to do here, I suspect that there is a potential win by being able to write not just UDFs, but like a user-defined join or something like that. But again, I need to think more about it. Just had 2 other things. And then the noisy data solution. In my mind, that's kind of what I was talking about. Like have the roboticist write the Rust functions and expose them as Python UDFs. That's kind of how I think. Here we go. Hopefully no questions. That's the way I like it. No. Yeah, go ahead.
Do you have any like real-time guarantees where some queries need to be executed within a few, I don't know, minutes?
No, but I'd love to. So
it is critical that some decision needs to be made before you take some action on
absolutely, but not in the data store. Like so when it comes to safety guarantees, if you put any kind of requirement on like off vehicle communication, so we don't do I should say we don't do database work inside on vehicle or more generally on robot. Is generally not done there for and there is a huge governing authorities on what it means to be safe, right? Safety critical, and basically safety critical operations must not rely on anything that could be interrupted, such as loss of, satellite or loss of cell signal or something like that. So generally doesn't have to be real time. We do some real time operations, but they don't need that kind of like low latency at this point. When I said I'd love to get it to the point where our ingestion system was so fast and so effective, and our queries were so effective that we were getting like real time analytics. Our analytics are pseudo real time. I mean, they're like seconds, seconds delayed. So, which is honestly for us right now good enough for everything we need to do. But I'd love to. But for safety critical things, absolutely not. Like hard no. But for everything else, I'd love to get to that point. And I guess in my other work, it was basically the same as what I have now. So, but I'm sure there are some people out there that do. Yeah.
So when you talked about the ingestion and how like Arrow and understanding of Parquet helped you save there, like what was specifics could you go into on like
sure
cube storage, what kind of
what
was the cost saving and what
the big cost saving was that I knew from our internal messaging system, I knew that I could write a program that would understand the schema and automatically convert it to one that would be compatible with Parquet storage. And then I had to like I was writing, so I wrote a C++ program, so I used the C interface for Arrow. you know, and like build a program that would automatically identify the schema, build out all of the necessary buffers, you know, pre-allocate enough memory storage, and figure out exactly at what point, because you have variable length arrays, so you have to figure out exactly, you know, how big should I make them, and at what point should I flush them, you know, and all of that. And the big problem was that the old version used, well, partially because it used Python, and it was doing some reflection. So like it had a process where it would look at the schema and it would do some reflection, and then it would use that to decode the data. So just like moving that from Python to native C or C++, that was a huge savings. But the bigger, the massive savings came from the fact that we no longer had to use this third-party vendor that was like streaming data. You know, and the thing I like about it is how much money it's saving. The other thing is it took our ingestion pipeline from basically about 48 hours to 45 minutes, which was made a lot of people very happy. So I don't know if that answers the question.
Yeah.
Cool. All right. There'll probably be more questions when it's like more database oriented talks then, I'm guessing. All right. Thank you all.
Thank you.